Hi everybody, welcome to the next lecture on audio coding. Today about the coding of stereophonic signals. So the goal here is to produce a spatial acoustic impression. So like in every day, when we hear a sound or noise, then we know where it comes from. So how does the brain actually do it? So the approach here is to look at information the ear is using, right? How does the brain and the ear decide from which direction a sound is coming? And this leads us to psychoacoustic effects. So the first effect here is the interaural time difference, short ITD. This comes from different ear arrival times due to different propagation paths. And this is one of the cues the brain is using to estimate the sound direction. So here you have a diagram. So here's a head from above. Here you have the nose and the two ears. Here you have a sound source, a little speaker. And you can see the distance from the speaker is closer to the left ear than it is to the right ear. And because of the limited speed of sound, the sound arrives a little bit later on the right ear. And this time difference tells the brain that the speaker is somewhat shifted to the left. Then the next effect is the interaural level difference, or short ILD. This comes from different sound pressure levels due to the shadowing of the head, particularly for high frequencies, which is the other cue the brain is using. So again, same setup. Here you have the head. Now the sound is coming a little bit more from the left-hand side, and you can see that the sound that is going from the speaker to the right ear needs to go around the head. So here the sound level on the right ear is somewhat lower than on the left ear, and this is another cue that the brain is using, particularly in cases where the time difference is hard to estimate, like when you have high frequency sounds. Then it's this is the dominant effect the brain is using. So then there's also the effect of the width of a sound, or apparent width. So we can have a very focused sound, but we can also have a more diffuse sound. And this comes from the coherence between different points in space. So this is measured by the interaural coherence, and this measures the degree of similarity between left and right signals at the ears, or when you say interchannel coherence, then it's the left and right channels. And for stereo, this is the most relevant part because usually we don't have the signals at the ear. So here we can see, instead of having a sound point, we have a sound cloud, right? And this sound cloud has varying width. And we perceive the sound at different width depending on the correlation that's coming from the different positions of this cloud. So if we have just these two speakers again, then these two speakers can create an impression of different sound width. If the sound of those two speakers is basically the same, but perhaps just multiplied by a factor as for ILD, then we perceive it as very distinct coming from a certain position. So this is the case 1. But if the sound from the two speakers is somewhat different, it's not just if one is the factor of the other, but maybe somewhat less correlated, somewhat different, then it appears more wide. And this is measured by this coherence, which you can see here. So basically this computes the magnitude of the cross correlation between the two speakers, left and right, divided or normalized by the autocorrelation for the left and the right. So if you have no correlation, for instance, if both speakers are just producing white noise, then you will have no cross correlation, and this term will become 0. Right? In this case, we have case 3. Here we would have a diffuse auditory object. So interchannel coherence would be 0. And that means we would have this sound cloud where noise is coming anywhere from this space. So no distinct object. On the other hand, if we have a cross correlation, which is very high, then the other extreme would be 1, right? If like one channel left is just a factor of the other, like for ILD, then we would have a cross correlation, and when we after we divide it by the autocorrelation of those two, we would have a factor or a result of 1. So then we have this distinct auditory object for IC equals 1, and then we have also in between cases. So imagine we have ILD plus some noise, and then it becomes more fuzzy. Right, so this is also important for parametric representation of spatial objects. So if you have objects which you want to recreate, given some parameters, then this interchannel coherence would be one of the parameters to tell the decoder how wide a spatial object is. Yeah, so first, where is ITD and ILD used? So the brain uses interaural time differences for localization at low frequencies, right? So here's the interaural time differences. So this is because for lower frequencies, the phase differences between different arrival times can be measured by the brain, right? If those phase differences are not too short, then the brain can measure them. But if we have higher and higher frequencies, then it becomes more difficult for the brain to measure those phase differences. And also you have this wraparound phenomenon. So if the delay, if you have a very short delay, even if you have a very short delay at a high frequencies, leads to a wraparound at 2 pi, and then it's not really accurate anymore. So that's why we have those two effects being applied at different frequencies. So at low frequencies, you have mostly the time differences and not much from the level differences. And this is also because at lower frequencies, the head is not doing much shadowing. The low frequency waves go easily around the head. At high frequencies, it's more difficult to estimate the red direction from the time differences, but it's becoming more easily for the level differences because the head is doing more shadowing. Yeah, so that the ILD and ITD can be interchanged within limits. So that's also why both are used in stereo. Yeah, so you can see the brain is using both, but at different frequencies they have different effectiveness. Also, there is something called the precedence effect or Haas effects. This means the brain remembers the direction from the time difference of the first wavefront, like from a wideband attack, like a drum, a castanet, or switching on a tone. So even if you have, say, a low frequency tone, which is switched on, then it arrives first at one ear and then at the other ear, and then this interchannel time difference kicks in, right? So the brain remembers even if it's a low frequency tone, and after that it doesn't really, I should say here, the high frequencies, if it's a high frequency tone, and even if it doesn't measure the phase differences anymore, it still remembers this first wavefront. Yeah, and these two effects are also used for recording. So the so-called delay stereo uses distant microphones, and for distant microphones you have time differences. So this is using ITD. So these microphones usually don't have much directionality, but because of their distances, their base here, you get different time arrivals, and that's why we have interaural time differences here. Then the other effect, ILD, is used by a stereo microphone pair, which is close together, usually in one case. but it has different directionalities. So those two microphones basically look into different directions. And that means we get different levels depending on where the sound source is positioned. So if the sound source here is closer to the left microphone, then the output of this left microphone will be higher than the output of this right microphone, where it's attenuated because of the directionality here. So this is using ILD, but not ITD because they're so close together. Yeah, so this leads us to coding. In coding, we also have quantization, and that means we get quantization distortion or noise. So now we have distortions from two channels, which are reproduced for the two ears. So now we also have the problem, where in space does this noise appear? Right. So if noise and signal come from the same apparent spatial position, this would be the optimum solution, because then the signal would mask the noise as we're used to. But if the signal and the quantization noise come from different spatial positions, then the quantization noise becomes more audible. So this is an interesting effect. It's actually not so obvious because it's still the same ears, but here the processing in the brain between the two ears come into play. And it actually can be significant. This is shown by the difference in masking levels between these two scenarios. The difference in the masking level, called binaural masking level difference, or short BMLD, is between 0 dB, which would be no problem, but it goes up to 18 dB. So that means the noise, which is off from the position of the sound, can be 18 dB more audible, or rather the masking threshold will be 18 dB lowered. So that's not good for coding. So here's an experiment to measure the BMLD. The masker, the audio signal, is identical to both ears, right? So it appears in the center. Then we have a test tone, the quantization noise, which is identical for both ears at the masking threshold, and it should be inaudible if we have the correct masking threshold. But then we do the same test, but with different phase relationships between the ears for the noise. And then it becomes audible, right? And that shows us that we have this unmasking because of this stereo effect. And this difference in masking threshold is called binary masking level difference. Binaural masking level difference. Yeah, so how do we use this in coding? The simplest method for stereo coding is to simply use separate channels for left and right. Problem here is, for instance, if we have an audio signal in the center, like if we have news, the speaker usually appears in left and right equally. So the signal appears in the center. But the quantization noise is usually uncorrelated between both sides because often the signal is not exactly identical to both channels, but has slight differences, and these slight differences cause different quantization noise or quantization error. And that means the quantization noise appears no longer in the center, but in the space around us. And that means unmasking can result from the binaural masking level difference. And also, the redundancy between the channels is not used for compression. So if we have this one speaker almost identical between left and right, and we have two channels which we transmit separately, then basically we transmit the same information twice. So that's wasteful. So that's why we have an alternative, the so-called mid-side coding. This using a matrixing, which is a sum and difference for left and right channel. So matrixing because we basically multiply a simple 2x2 matrix to our left and right channels. So here you can see the effect. For encoding, we compute the mid-channel as left plus right divided by 2. So this is the average. This would be the center channel, the mid-channel. And then we have the S, the side channel, which would be the difference left minus right divided by 2. And in the decoder, we would reverse this process. Left would be mid plus side. You can see the L adds up and the R cancels. And for the right, we would have mid minus side. You can see the left would cancel and the R would add up. So this is invertible in the absence of quantization. But the quantization noise, when you look at it, we have an addition of noise powers. So mid and side are quantized, and that means in the process of coding and decoding, we add quantization noise or quantization errors. So basically random noise. And if we add two noises, we add the noise powers, right? Because of the energy conservation. So you could imagine each noise as coming from a certain heat distribution, and then if we add two of those heat distributions, two of those noises, each of those heats has a certain energy. In the end, we have the addition of those energy. And that means we have a factor of square root of 2 for the signal voltages. Right, so we now have an increase of our quantization noise. So that also shows that we now need to decrease the quantization noise. So that would be similar to the BMLD, which would require us to lower the masking threshold. So here you can see the mid-side coding as a plane of left and right samples. So here on the horizontal axis you have the left sample, and on the vertical axis you have the right sample. And if we have a signal which is in the center, like a news broadcast, then all those samples will be very similar between left and right. And this is what you can see here. So if it's on this diagonal, this M diagonal, most samples will be close to this M axis. And on the S axis, you would not have much. Right. So that shows also why it's useful to do this mid-side for centered signal, because then most of the signal pairs will then be along the M axis, but not much along the S axis. So for a centered signal, side S would be 0 or close to 0. And that means we have fewer bits. Bits for the side channels are minimized. And because of that, we have little quantization distortion from the side. So remember, this is also good because we have the addition of the noises. And if there's not much from the side channel, not much noise, then we also don't have much noise increase. Also, we have a reduced bit rate, because if there's not much in the side channel, then because of entropy coding, there will be not many bits left, the redundancy reduction here. And also the quantization noise would be centered, like the signal, because the quantization noise would be caused by the mid-channel. And this works for predominantly centered signals. So if you have a news broadcast, then mid-side works fine. But the problem is that this doesn't work for signals which are off the center, right? Assume a signal with amplitude A is only in the left channel, right? So this is basically the opposite of our assumption for the center. So everything is left, nothing is on the right channel. Then we do the matrixing and quantization with quantization noises N1 and N2. Then we would have the mid channel would be a half, because R is 0, so all what's left is A. L plus R over 2 is A over 2 in this case, plus some noise. Similar for the side would be A over 2 plus noise 2 here. And yeah, now we have unnecessary bits needed since now both have a significant signal, right? Mid and side are both significant. Plus here in the decoder, we would now use the dematrixing. So we would take our equations that we had before. Left is m plus side, right is m minus side. Right, left is mid plus side, so all what's left here is here a half plus a half, but now plus the two noises, plus n1 and plus n2. Similar for r, but for r we would have the difference, so the a would cancel and what's left is n1 plus minus n1 minus n2, as you can see here. And since the side channel usually is not identical to 0, we would have slight differences in the ends, right? And that means we have different noise powers. So here we have the square root of 2, but also this difference here, the minus, if you have one noise minus the other noise, it doesn't cancel. It's the same as plus, right? So it's the same noise power as n1 minus n2. And that means here, now in the right channel, where we originally had almost nothing, we now have the same noise as in the left channel. So that's not good, right? We have the spreading of the noise. And that obviously becomes then audible. Yeah, that means hence for signals with little correlation between the channels, we switch to separate left-right coding if necessary. Right, so this is a case where we have little correlation between the channels. So here we don't want to use mid-side, but we want to keep separate left-right coding. Yeah, and this can be seen here in this diagram. We start here in the encoder with the left and the right input. And then we have this matrixing. Here we can see here's the mid channel, left plus right. The 1/2 is omitted here. And here we would have right minus left. Again, 1/2, the factor is omitted. And here we have a kind of a funny switch. So here you should imagine it's either one of the two positions. Here it's drawn as both would be going through, but it's actually one or the other. Right? So either we have left right, that would be this position here, left right, or we would, no, this would be mid-side. So if this line goes through, we would have mid-side. And if it's on this diagonal position, then we would have separate right and left coding. Right, so we switch depending on the signal. If left and right are very similar, then we would apply mid-side coding. If left and right are very different, we would apply left-right separate coding here. Yeah, and we also need to transmit this decision information to the decoder so that it does the unmatrixing only for the mid-side case. So the mid-side is when it applies here this kind of butterfly structure. Right, so that's simple enough. Basically the encoder needs to decide what's best and then tells the decoder. Yeah, so this would be for the entire audio signal, but usually you have a mix of signals and different instruments and different sources coming from different directions in space. For instance, in music, often the singer is in the center, so mid-side would be appropriate. But for instance, the guitar or the drums come from the sides, so they are separate, left-right would be more suitable. And to take that into account, we do the switching not on the full audio signal, but in the subbands. Right? So for instance, the MDCT subbands of the encoder. Remember, the MDCT subbands are very fine, and you can imagine different subbands carry components from different sources. So one subband you can say is say guitars, another subband belongs to the singer, and then in this way you can separate different sources as much as the ear needs it. Right, and what you actually do is you don't do the decision for individual subbands of the MDCT, but basically you do it for the scale factor bands. Yeah, so we have mid-side coding for higher quality, but the goal for intensity coding would be to reduce the overhead for stereo for bit reduction. So this is basically a simplification for stereo coding. So instead of having really two different signals that we transmit basically the mid-channel and side information. Right. So in lossy coding we use interaural level differences, ILD, meaning just level differences between left and right, or intensity stereo. Right. So basically we don't use ITD anymore, just ILD, and for ILD we can just transmit a factor. Right? We can say for this subband we have this factor for left and this factor for right. And this can be easily used above, say, 4 kilohertz, because that's where the ear is using only ILD anyway. Yeah, so here you can see the example of an intensity stereo encoder. Here we have the left and right channels, subband decomposition. So this would be either MDCT or in the newer coders, it would be a separate QMF filter bank, for instance. Then we have a phase adjustment. Basically, this ensures us that we have really level differences and not time differences, right? Remember, in intensity, we cannot really deal with time differences or phase differences. And after this adjustment, we can simply sum left and right to obtain the center channel, the coupling channel, or mono, right? So here we have the sum. This would be basically the mid channel, but here we also now have a phased adjustment to get rid of any time differences. So here we measure power of the center channel, and also we measure the power of the side channels here, or the left and right. And then we just compute the factors for the left and right scaling, right? So we have now this mono channel, and then we have factors for right and left. So what comes out here is basically the center with different factors for left and right, exactly what ILD is doing, the interaural level differences. Yeah, and this is how the decoder decodes it. It takes the coupling channel, which contains the audio signal, and then it multiplies it with different factors for left and right, depending on where in space the signal appears. And it does it for every subband. So it could be either, again, the synthesis MDCT or the synthesis QMF in newer parametric stereo standards. Yeah, and that leads me to parametric stereo. So that's supported within MPEG 4 within the high efficiency AAC, the high efficiency profile. And it delivers good quality at bit rates as low as 24 to 32 kilobits per second. So that's pretty low. And excellent quality around 48 kilobits per second on a MASHRA score. MASHRA is for multi-stimulus with hidden reference and anchors from this ITU standard. And this is part of the current state-of-the-art MPEG audio coders. Yeah, so here you can see how it's working. We have the time signal. Here we have our time frequency resolution. So this is usually how we know it. Window switching in case of transients. And here you can see the hybrid QMF analysis. So here comes the QMF filter bank. So we have a two-stage hybrid quadrature mirror analysis filter bank. So this uses a QMF, and this is an extension of the filter bank used in spectral band replication, which is a parametric representation for high frequencies. Right, so it uses basically the same type of filter bank. An incoherent signal is generated by the decorrelator D by convolution of the mono input with an all-pass filter. So here you can see it. We have the signal, and then we have a decorrelator. So this is to obtain wide sources in space, right? or to encode white sources in space. So it basically takes the audio signal and passes it through an all-pass filter. And remember, all-pass filter have different group delays for different frequencies, and this is how it basically decorrelates the signal. So instead of adding noise, you would just have different group delays for different frequencies. Yeah, and then we have the matrixing, which is a mixing and phase adjustment process here. And then we have a two-stage hybrid QMF synthesis here. Right, and out comes two signals, X1 and X2. Yeah, so here the structure of the QMF filter banks. We have the lowest QMF subbands are filtered through a subfilter bank of order n in order to enhance the frequency resolution, and the remaining subbands, the signals are delayed by n/2 samples to compensate for the delay. So here we have a higher resolution for the lower frequencies, and the rest is just delayed. Yeah, and here we have the synthesis. So here we basically have the inverse structure, summing up different subbands, and then here we have the QMF synthesis. Yeah, so here we have the parametric stereo in high efficiency AAC. Spectral band replication and parametric stereo operate in virtually the same QMF domain, so this is very practical because it's very effective combination resulting in significant complexity reduction. And the delay in SBR process is identical to the delay caused by the subfilter bank. So here we would have the decoder. So here's the demultiplexer, here we have the AAC decoder, then the QMF, here the subfilter banks, here the generation of the high frequencies, here the parametric stereo with the different factors, and finally the QMF synthesis filter banks to output the stereo here. So also observe that we have no ITDs, right? It's really all level differences which this uses. Level differences and coherence. Yeah, and this can be extended to surround. Since we have a parametric representation of stereo, it's actually straightforward to extend it to more channels to have surround or spatial audio. So this is based on parametric stereo. The spatial parameters enable modification of certain aspects of the downmix. We have matrix surround compatibility. We have also artistic downmixes. We have binaural rendering possible. And the channel configuration of the encoder can be different from the channel configuration of the spatial decoder. For instance, rendering of 4.0 from a 5.1 signal configuration without having to decode all 5.1 channels first. So we can just do it by different matrixings. And residual coding, which means we have an enhancement layer, is possible to enable MPS to surround to support higher quality. Right, so here we would add an enhancement channel to get better quality, but I think this is hardly used. Yeah, so here we have some elementary building blocks for Ampex surround. Here we have some signal input. For instance, here either mono or stereo, two additional channels. We have parameters input and output, and here we have the signal output. Here we have an encoder which takes, for instance, 2-to-1, which means stereo to mono, or 3-to-2, which means 3 input channels to stereo. And then on the decoding side, the same configuration, so either mono to stereo or stereo to 3 channels with site information. And here you can see how we can combine them into different structures to obtain different configurations for surround and playback. So here is an example for downmix to mono. So you can see we have the center channel, low frequency enhancement. Then we have left and right forward, left and right sides. So here we have 5.1 plus this center and low, well, these are 5 plus some enhancement, low frequency enhancement. Yeah, here we would have the same input, but downmix it to stereo. Here we would have just mono plus some site information. Here we have stereo plus some site information. Yeah, and these PX here, which you can see, P2, 4, 3, and so on, are parameter sets with spatial information. So this contains the information about the factors that we need and for the coherence. Yeah, similar for the upmix. Here we have the parameters as input again, and we have the inverse structure. So here the upmix from mono, and here the upmix from stereo. So it's actually quite versatile. Yeah, so in MPEG surround we have matrix surround conversion block. This is a method to create a pseudo surround experience based on a stereo downmix with specific downmix properties. So this is more generic than we just saw, 5.1 for instance. Here it's surround, so it's not specified with a number of channels. We have a conversion from conventional downmix to matrix downmix. This is a post-processing stage of the encoding tree. And conventionally we downmix such that the surround signals are in anti-phase, and that means it's impossible to retrieve the original input channels. Then we have the MTX conversion, which is dynamically varying, with an invertible matrix. This depends on the spatial parameters. The decoder can undo the processing. So we have the choice. Then we have the coding of the residual signal. So the TTO and the TTT encoding can create residual signals. They can be bit efficiently encoded and transmitted along with downmix and spatial parameters, and this allows full waveform reconstruction. But as I say, I think it's hardly used. So here you can see some applications, what is used where. So here we see mid-side full band. This is the oldest method, and this is used in MP3, the oldest coder here, and in lossless coders. Lossless coder because there you want to be able to invert it exactly. MPEG is a coder which is not really used anymore. This is, was a coder which was an alternative to AAC by Lucent Alcatel. Here we can see mid-side subband. So you can see this is used by the newer coders, AAC and AC3 and also PEG. Then intensity stereo is used by all of them. Then parametric stereo is used by AAC, and MPEG surround is used by AAC, AC3 and MP3. Yeah, so this leads me to my conclusions. Mid-side stereo is the most widely used stereo tool, used at medium bit rates and above, and it produces a lossless stereo image, or it can produce a lossless stereo image. Intensity stereo is used at lower bit rates. It is lossy because ITD is not used, and the stereo image can lose detail, again from not using ITD. Then MPEG surround is the most recent development. It allows low bitrate and multi-channel audio, and it also has backwards compatibility with stereo coders. So here's some literature: Brabart, Faller, spatial audio processing, MPEG surround, and other applications from Wiley in 2007. Okay, so this leads me to the end of this video. Thank you for your attention, and then see you next time.